Every photometric result your analyzer reports, glucose, creatinine, bilirubin, every colorimetric assay, comes down to one 1852 equation. Before you trust that number, you should understand exactly what it's measuring, and exactly where it starts to lie to you. This is a deep technical walkthrough for the people who actually run and maintain photometric instruments, from the law itself to why it breaks down, to the optics and detectors built to work around those limits. Here's the law itself. Absorbance equals the molar absorptivity of your chromophore, multiplied by concentration, multiplied by the path length the light travels through the sample. Every colorimetric assay on your analyzer is this equation solved backward for concentration. Molar absorptivity, epsilon, is a fixed physical constant for a given chromophore at a given wavelength. It tells you how strongly that specific molecule absorbs light. It's why every colorimetric method specifies an exact wavelength. Change the wavelength and you change epsilon entirely. The other half of the picture is transmittance, the fraction of incident light that actually makes it through your sample to the detector. Transmittance equals the light intensity leaving the sample, divided by the intensity that entered it. Every chromophore has an absorption spectrum, a curve of absorbance across wavelength, and every method is built around its peak, lambda max. That's not arbitrary. Sensitivity is highest there, and critically, the curve is relatively flat at the peak, so small wavelength drift barely changes your reading. So 4 things determine every absorbance reading you'll ever see on a chemistry analyzer: the chromophore's identity, its concentration, the path length of the cuvette, and the wavelength you chose to read it at. Run the numbers on a real assay. Measure an absorbance of 0.622 at 340 nanometers for an ADH, with a 1 centimeter path length and epsilon of 6,220. Solve the equation backward and you get a concentration of exactly 0.1 millimoles per liter. Everything downstream of this, every enzyme assay, every colorimetric test on your analyzer, is this equation, applied at a specific wavelength, solved for the one unknown you actually care about, concentration. Now, your detector doesn't actually measure absorbance directly. It measures light intensity, which the instrument converts to transmittance, then to absorbance using a logarithm. Absorbance equals the negative log base 10 of transmittance. Here's why that logarithm matters. Plot absorbance against transmittance directly, and the relationship is sharply nonlinear. Most of the useful measurement range is compressed into a narrow slice near 0% transmittance, which is exactly why you never see a clinical analyzer report results in raw %T. Put the 2 scales side by side and the payoff of using absorbance becomes obvious. Absorbance rises in a straight line with concentration. That's what Beer's law promises. Transmittance falls off exponentially, which means equal steps in concentration do not produce equal steps in your raw signal. There's a deeper reason to care about this. Plot the relative photometric error in your calculated concentration against transmittance, and you get a U-shaped curve. Error is high at both very low and very high transmittance, with a sharp minimum sitting right around 37%. That minimum error point at 37% transmittance corresponds to an absorbance of exactly 0.434. It's why well-designed assays are calibrated so the clinically relevant concentration range lands your absorbance somewhere between roughly 0.1 and 1.0, the sweet spot where your instrument's precision is actually trustworthy. This is why diluting a sample matters more than it sounds. Push an assay's absorbance up past 1.5 or 2.0, and you're not just risking nonlinearity from the chemistry, you're operating in the high error tail of this curve, where small optical noise translates into large concentration errors. So as a working rule, most clinical photometric assays are designed and validated to keep results within an absorbance window of roughly 0.1 to 1.0, comfortably straddling that 0.434 optimum. Absorbance isn't just a mathematically convenient unit, it's the scale on which your instrument's measurement precision is actually optimized. Reading raw transmittance would waste that precision entirely. Here's a dangerous assumption worth killing early. Doubling concentration always doubles absorbance. That's only true within a limited, validated range. Push far enough in either direction and Beer's law quietly stops holding. Deviations from linearity fall into 3 buckets. Real deviations, where the chemistry itself changes at high concentration. Chemical deviations, where the absorbing species shifts equilibrium, dissociating, associating, or forming new complexes. And instrumental deviations, largely driven by stray light and non-monochromatic light in your optical path. Here's what that looks like on a real calibration curve. The low to mid concentration points sit right on the line Beer's law predicts. push into the high range and the curve bends away, usually downward, reading lower absorbance than a truly linear relationship would predict. The single biggest instrumental culprit is stray light, light that reaches your detector without actually passing through the sample, whether by internal reflection or scatter. It puts a floor under how low your measured transmittance can ever read, no matter how concentrated the sample is. That gives you two distinct failure signatures. Stray light produces a negative deviation. Measured absorbance reads lower than Beer's law predicts. Chemical association at high concentration typically produces a positive deviation instead. Absorbance rises faster than concentration alone would justify. This is exactly what a linearity verification study is designed to catch. Run a dilution series against expected concentrations, plot the difference between measured and expected at each level, and any systematic drift outside your acceptance limits flags the point where your assay leaves its validated linear range. A proper linearity check follows a set pattern. Use a sample or dilution series spanning your full reportable range, run each level in replicate, plot measured against expected concentration, and flag any point where the deviation exceeds your predefined acceptance criteria. Beer's law isn't wrong. It's a first-order approximation that holds beautifully within a defined range. Knowing exactly where that range ends is the difference between a trustworthy result and a quietly wrong one. So how does the instrument actually generate that absorbance reading? Every photometer follows the same basic light path. A source generates broad-spectrum light, a wavelength selector isolates the band you need, that light passes through the sample, and a detector measures what's left. Light sources vary by instrument generation. Tungsten-halogen lamps give a broad, continuous spectrum across the visible range and remain the workhorse of most chemistry analyzers. Deuterium lamps extend that coverage into the UV. And LED arrays, tuned to specific clinical wavelengths, are increasingly replacing both. The practical difference shows up in the output spectrum. A tungsten-halogen lamp spreads its energy thinly across a huge range. An LED concentrates nearly all its output into a narrow 10 to 30 nanometer band centered exactly where your assay needs it. More signal, less wasted light, and none of the warm-up drift of a filament bulb. For isolating your wavelength, you have two broad approaches. Interference filters give you a fixed, narrow bandpass, cheap, robust, but locked to one wavelength per filter. Diffraction grating monochromators let you dial in any wavelength continuously, at the cost of more moving parts and more complexity. Zoom out and wavelength selection splits into a clear family tree. Filters, either broad absorption glass filters or narrower interference filters, versus true monochromators, built around either a prism or, far more commonly today, a diffraction grating. On the detection side, silicon photodiodes are the standard workhorse, robust, linear, inexpensive. Photomultiplier tubes step in when you need extreme sensitivity to faint light like nephelometry, and diode arrays capture an entire spectrum simultaneously, all in one exposure. The bandpass difference between these devices really matters. A typical interference filter passes roughly 10 nanometers of light, while a good grating monochromator can narrow that down to 1 or 2, and a narrower bandpass means less error from polychromatic light hitting a sloped absorption curve. This ties straight back to the stray light problem from earlier. A wide bandpass or a poorly maintained monochromator lets in more off-target wavelengths, which is exactly the mechanism behind negative deviation from Beer's law at high absorbance. Source, wavelength selector, detector, every choice in that chain either protects or erodes the linear relationship Beer's law promises you. Quick pause. If this breakdown is helping you, take a second to hit like and subscribe. It genuinely takes a lot of effort to make videos like this, and your support keeps them coming. Cuvette material matters more than people assume. Quartz stays optically clear all the way down to about 190 nanometers, into the deep UV. Ordinary glass and plastic start absorbing below roughly 320 nanometers, which makes them useless for a UV-based enzyme assay reading NADH at 340. Path length matters just as directly, because it sits right in the Beer-Lambert equation. Have your cuvette's path length from the standard 1 centimeter down to half a centimeter for a microvolume sample, and with everything else unchanged, your measured absorbance drops by exactly half. Automated analyzers mostly avoid disposable cuvettes entirely, using either a fixed flow cell that gets rinsed between every sample, or a rotor of individual reusable cuvette positions that cycle through a wash and dry station on every run. Because path length is a direct multiplier in the equation, most manufacturers hold cuvette path length tolerance to well under 1%. A tiny mechanical error there translates directly into a proportional error in every result. Before trusting any run, a quick physical check of the cuvette pathway pays off. Confirm there's no visible scratching or fingerprint on the optical faces. Check for trapped air bubbles in a flow cell, and verify the blank reading matches your instrument's expected baseline. Build that into a standing QC habit rather than a one-off check. Verify cuvette cleanliness, confirm matched path length across a cuvette set, and log any blank drift over time so a slowly fouling optical path gets caught before it affects patient results. A cuvette isn't just glassware, it's a physical variable sitting directly inside the Beer-Lambert equation, and it deserves the same QC discipline as your reagents. Everything so far assumes light travels straight through a clear solution. Now flip the geometry entirely. This is the physics behind dry slide chemistry, the technology underneath your dry chemistry bench. In a dry slide system, light hits the surface of a multi-layer reagent slide, scatters and partially absorbs as it travels through the layers, and a portion bounces back out toward a detector position to catch that reflected light, not light that passed all the way through. Because that slide scatters light as much as it absorbs it, the simple Beer-Lambert transmission model doesn't apply. Instead, reflectance photometry uses the Kubelka-Munk function, which relates diffuse reflectance to the ratio of the absorption coefficient over the scattering coefficient, the reflectance analog of Beer's law. Line the two technologies up directly. Wet chemistry passes light through a homogeneous liquid and follows Beer-Lambert exactly. Dry chemistry bounces light off a scattering, layered solid and follows Kubelka-Munk instead. Different physics, same underlying goal of turning light into a concentration. A dry slide is engineered in microscopic layers. A spreading layer that evenly distributes the sample and filters out interference like red cells. A reagent layer where the actual color-producing chemistry happens, and a support layer underneath holding the whole structure together. Raw reflectance plotted against concentration curves sharply, nowhere near the straight line Beer's law gives you. Run that same data through the Kubelka-Munk transform, though, and the relationship straightens out into something you can calibrate against, just like absorbance. The practical payoff of all this physics. Dry chemistry needs only microliters of sample, skips liquid reagent prep and cuvette washing entirely, and gives reagents a much longer shelf life, which is exactly why it dominates point-of-care and low-resource testing. Reflectance photometry isn't a workaround or an approximation of transmission photometry. It's a physically distinct measurement principle, engineered specifically for a scattering medium that transmission optics were never built to handle. One more light-based technology worth knowing cold. Turbidity, the cloudiness of a solution caused by suspended particles scattering light, the physical basis of every immunoturbidimetric assay on your analyzer, from CRP to rheumatoid factor. Turbidimetry measures this the simplest way possible. It reuses standard photometer geometry, positioning the detector directly in line with the light source, and measures how much the transmitted beam is reduced by particles scattering light out of that straight path. Nephelometry takes a different geometry entirely. Its detector sits off to the side, typically at 90 degrees, catching light that particles scattered away from the main beam. That off-axis view gives it far better sensitivity at low particle concentrations, at the cost of needing dedicated, more specialized optics. Both techniques share one dangerous pitfall, the prozone or antigen excess effect. At very high antigen concentration, small non-scattering soluble complexes form instead of large lattice complexes, and scattering paradoxically drops, risking a falsely low result on your highest, most critical samples. Plotted out, this produces a dose-response curve that rises with concentration, peaks, and then bends back downward at very high antigen levels. A hook shape that can silently mask a critically abnormal result if your instrument isn't specifically checking for it. In practice, immunoturbidimetric and immunonephelometric methods cover a wide panel of clinically important proteins. CRP, rheumatoid factor, complement C3 and C4, immunoglobulins, and microalbumin all run on this exact light scattering principle. Weigh the two technologies against each other honestly. Turbidimetry runs on ordinary chemistry analyzer optics, keeping cost and complexity low. Nephelometry needs dedicated hardware, but rewards you with meaningfully better sensitivity right where low concentration precision matters most. Turbidimetry and nephelometry are really the same underlying phenomenon, light scattering, measured from two different angles, and the angle you choose trades sensitivity against simplicity. Let's close with a real troubleshooting scenario. A creatinine assay's calibration curve looks perfectly linear at low to mid concentrations, but flattens out at the high end. A patient sample with markedly elevated creatinine keeps coming back lower than a manually diluted repeat confirms it should be. Work the decision the way technical staff actually should. Does the curve flatten near the instrument's known absorbance ceiling? If yes, suspect stray light or bandpass first. If the deviation instead tracks with a specific chemistry like a known dimerization reaction, suspect a real chemical deviation. The formal fix follows CLSI EP6 linearity verification logic. Run a dilution series across the full reportable range, fit both a linear and a higher order polynomial to the data, and if the higher order term is statistically significant, that's your objective evidence of true nonlinearity. After restricting the reportable range and implementing auto-dilution, the repeat linearity study came back with an R-squared of 0.998 across the full clinical range, comfortably above the 0.95 threshold most labs require to sign off a corrected method. When you're troubleshooting a similar deviation yourself, work through it in order. Confirm the calibration curve's shape objectively, check for stray light with a cutoff filter, verify wavelength accuracy, consider an alternate reading wavelength if interference is suspected, and restrict the reportable range until it's resolved. Keep this framing in your head every time you look at a raw absorbance number. It's not just a reading, it's the output of an equation that only tells the truth inside a range you're responsible for knowing. Quick check before we close. Based on the photometric error curve we covered earlier, at what approximate percent transmittance is the relative concentration error at its statistical minimum? Carry these four numbers back to the bench. 0.434 as your optimal absorbance, roughly 0.1 to 1.0 as your practical linear window, 190 nanometers as Quartz's UV cutoff, and 90 degrees as nephelometry's classic scatter detection angle. Whether light passes through a cuvette, bounces off a dry slide, or scatters off immune complexes, it's still the same underlying physics. And understanding it is what turns you from someone who runs the analyzer into someone who can actually trust and troubleshoot what it tells you. Here are the key references and sources for this video. Thanks so much for watching. If this helped, like the video and subscribe for more clear, simple explainers, and I'll see you in the next one.